Hello and welcome to this video about point dipoles. I've already made another video about them, but I'd like to approach these things in a different way this time. I'd like to find the voltage produced by them and use vector calculus to find the electric field from this voltage. I'd also like to show that they are linear, so that they may be divided up into x and y components the way most other vectors are. So to begin with, here's the derivation of the distances of the point A away from the centre of this dipole, which is a point dipole, when epsilon approaches 0, but doesn't actually equal 0. I've done these calculations in the last video, and you can easily see from the geometry and calculus that these are the correct expressions for the distances. Now to derive the voltage. This is the equation used to find the voltage in the vicinity of a monopolar electric charge. Then, after substituting the distance in from the positive charge, we get this expression. We get the voltage from the negative charge using a similar method. To get the voltage from both charges, we have to add them together. Voltages can be added like scalars, and no x or y components have to be found. So the calculations are much easier than those for electric fields. And substituting these values in gives us this expression. We'll use fractional addition rules to give us this even more complicated looking expression. But now this expression has only one common denominator. The term containing epsilon squared can be eliminated using the rules of calculus. We can factor out the r term. The difference of square roots gives us this. Then we can multiply all of the occurrences of r together. I'll just write these equations out again at the top. This is what the dipole moment is equal to. We'll substitute it back into this equation to give us this. This dot product of vectors is equal to this expression. I want to write the vectors in the colour red, so that vectors can be distinguished from scalars, and especially that the vector r can be distinguished from the scalar of r. These vectors can stand for any two vectors that have an angle of theta between them, and theta can be the angle corresponding to its latitudinal position in spherical coordinates. Substituting this expression into this other one gives us this compact formula for voltage. So just looking at what the vectors r and p are, and the angle theta, r is any vector that is at an angle of theta to p, and all possible values of r scribe a circle at the top of a sphere representing spherical coordinates. The angle phi at the top determines which particular r it is, and for the purposes of this video it is redundant, but it is good to know what its purpose is in spherical coordinates. Now to derive the electric field from the voltage using vector calculus. This is what the voltage is equal to in terms of these two vectors. This is what the electric field is equal to in terms of the voltage and using vector calculus. The electric field is equal to the gradient of the voltage multiplied by -1. Substituting the first equation into the second gives us this. Then we can do this subtle step, since r hat is equal to the vector r divided by the scalar value of r. Expanding this expression using the product rule for gradients gives us this. The gradient operator operates on r and not on p, because r represents the position of something in space and p doesn't. And then we can manipulate this equation into this more presentable form. And here's a method of finding the electric field in spherical coordinates. The vector dot product is equal to this trigonometric identity, where p is the scalar magnitude of the dipole moment, and theta is the angle between the two vectors. So substituting the second equation into the first gives us this equation for v in spherical coordinates, which is independent of the second angle phi. This is what the electric field is in terms of the voltage in space. And substituting the third equation into the fourth gives us this equation. So then we perform the gradient operation in spherical coordinates on this function, and it looks like this. And because this equation is completely independent of the angle phi, which is a sort of longitudinal angle, this term equates to 0. And solving the partial differential equations gives us this vector equation. Simplifying this equation gives us this solution. I'll just keep the film running for a little while to let you meditate on it and to let it sink in. Now to show that the point dipoles are linear. To do this, we only need to show that the electric fields that they induce are linear. So we firstly define these 2 point dipoles that are found in the same location in space, P and Q. We firstly have to show that this equation is true. So this is what the electric fields are found to be from their derivation. We can gather all of these numerator terms over the one denominator, and we can gather all of the terms together like this. P and Q can be gathered together in brackets immediately. We can factor out this number and unit vector term. Then we can factor out this second unit vector term. So then this is equal to the electric field induced by these 2 dipoles added together. So we have proven the first part of this theorem. Now to prove the second part of the theorem, we define A to be a real number. We have to prove that this equation is true. This is what the right-hand side is equal to according to what we have already derived. And we can expand this expression so that A is in the fraction. Then we can bring A all the way in next to P. So this proves that this second expression is true. So we have shown that the dipole is linear, and thus that dipoles can be added and subtracted from each other as though they were vectors. So thank you for watching this video, and I wish you all the best in your efforts to study this sort of electromagnetism.